So this video, we're going to talk about the linear momentum equation. We're going to kind of talk about it, first setting up the equation into its two components. We're going to talk about the sum of forces onto the system, and then we're going to do a couple of examples. So we're in chapter 6 of our Sengel fluid mechanics book. And we're going to talk about the linear momentum equation. So with this particular equation, we have to break it into two components. We have to think about components in the x direction and the y direction. And we must consider these components relative to our datum. So the datum that I'm always going to be using is positive up in the y direction and positive right in the x direction. Okay, so these are the linear momentum equations where we have the sum of forces onto the system is in balance with density, directional velocity, the area, the magnitude of the velocity in the x direction, and these are all out of the system minus the sum density multiplied by our directional velocity multiplied by our area multiplied by our magnitude of our velocity, and these are all in. Okay, so again, this is going to be sum out of our system minus into our system. I did leave kind of like a little space there. It's because typically we would also include this momentum correction factor. It's not always needed. So that for the sake of this video, we're essentially going to say that this is unity. So we're not going to be considering this correction factor in this video. Okay, so these are the components in the x direction. Then we also have our sum of the forces onto the system in the y direction is equal to density multiplied by the directional velocity directional velocity multiplied by area multiplied by our velocity y, again, out the system, minus the sum density directional velocity y, a magnitude velocity in. So again, these are all out of the system is in balance with what comes into the system. You must make sure that you consider that this is a directional velocity. So again, if you have some movement, so let's say you have some pipe exiting at some angle. So let's say it's entering this way and exiting that way, okay? Now, if you look at this entrance here, so this is my in, okay? We have no y component, right? We only have Vx, where Vy is equal to 0. Let's say this is 1, so this is V1x, V1y, okay? And let's say this is 2, and this is out. So then we would have to break this velocity vector into its two components. So this is V2, this is V2y, and this is V2x. And if you have some angle here, you must consider that angle where V2x is going to be V2, and this is going to be cosine theta. V2y is going to be V2 sine theta. So you must make sure that you are considering whether there is some angle. You must make sure you break your X and Y components down, because you're going to need to do that for each of these equation setups. Again, the magnitude, so this velocity value here is just the magnitude. So it would just be, for instance, we're talking about the in this case, this would just be V1. We're going to do examples showing this. Now let's talk a little bit about the left-hand side of the equation, the sum of forces onto the system. So the sum of the forces onto the system is going to be considering sum of forces due to gravity, the sum of forces due to pressure, the sum of forces due to viscous effects, and the sum of forces due to other. I'm going to write a couple examples on the bottom here. So the sum of forces on the system, this is true in either the X or the Y direction, okay? So this is true, regardless of the direction, okay? Gravity, right, this is pretty obvious. We're talking about our weight, and this could be weight of water, weight of a nozzle, weight of a pipe, weight of whatever is acting onto the system, okay? Pressure, this is talking about your piezometric or your hydrostatic pressure, right? Where your pressure at those ends, you can find using gamma H, right? So P is equal to gamma H. So what is force going to be? Force is going to be pressure multiplied by area, which is gamma HA, okay? And also what happens is sometimes the pressure is given, such as there's some kind of gauge pressure. So you would just multiply that gauge pressure by the cross-sectional area, and that will give you the force at that location. Now, something to keep in mind is this, I call it my Chinese finger trap rule. So if I redraw this configuration down here, okay, you have flow going in and out, but that is not how you draw your pressure forces, okay? So your pressure forces are going to be acting onto the system in this direction, like similar to your Chinese finger trap, where you enter your fingers into both ends, and that's where your fingers are pointing, that's the direction of the force. So this would be force at 1, and this would be force at 2, okay? And again, similar with the velocities, you'd have your directional forces you have to break down, okay? Okay, viscous effects would be if you have any forces due to friction. Of course, if you have flow going into the pipe and it's moving from 1 to 2, then your friction force would be going in the opposite direction here, something like that. And then other, this is usually what you're solving for, not always, but usually this would be your reaction forces. So for instance, this pipe that we have here isn't just kind of standing alone on itself, right? There has to be some support. Okay, some support that's keeping that pipe stationary. So the support would be similar to having some reaction forces. So this would be the reaction in the Y direction, and this would be the reaction in the X direction, okay? So that's an example of reaction forces. Other forces are also considered tension. You could have a setup where you have a rope or things like that. So just make sure that you carefully make sure you note that. Okay. Again, what I'm going to do for my systematic approach is I'm going to make sure we draw our free body diagram, right? So similar to what you did in statics, and that's to help with the sum of forces onto the system. Okay. And then I'm also going to draw what I call a velocity diagram, which is similar to this diagram here. And that actually helps us break down our directional velocities relative to the datum. Okay, it's incredibly helpful doing that. Okay, so let's go ahead and get started and do an example. So let's start a fresh page. Okay. So we have exhaust, and we're going to assume properties of air, leaves a 4-foot diameter chimney with a speed of 6 feet per second because of the wind after a few feet downstream. The exhaust flows in a horizontal direction with a speed of 15 feet per second. Determine the horizontal component of the force that the blowing wind puts on the exhaust. Okay, so let's go ahead and draw the setup here. Make that a little smaller so you can see the whole problem statement. Okay, so we have some, right, exhaust you can draw for fun. Maybe like the Simpsons cartoon here. So you have some exhaust that's going out here and it's getting caught by the wind. So there's some prevailing wind going in this direction that's then causing the exhaust to make kind of an abrupt turn. Okay. So it's going out and then it makes an abrupt turn here. Okay. Now, according to some measurements, we have uniform velocity at this measurement, at this location, and it is 15 feet per second. So it says here, right here, right? It's 15 feet per second, okay? We have the prevailing wind speed, so it says here, the chimney has a speed of 6 feet per second. So this is exiting here at 6 feet per second. Again, uniform. It's kind of the uniform, sorry, the universal symbol for uniform. Okay, let's see. This is all still provided in the in the picture. I'm just also trying to correlate that with the what's in writing here. We have a 4-foot diameter chimney, okay? And it looks like that is it. Let's see here. Okay, so let's see what else is given. Okay, let's see what else is given. So we're given that we're supposed to assume air properties. So air properties, which helps us because we need those air properties in order to calculate our linear momentum equation. So the density of air is going to be 2.38 multiplied by 10 to the minus 3 slugs per feet cubed. Okay, that's our fluid property. So exhaust leaves a 4-foot diameter chimney with a speed of 6 feet per second. Because of the wind, after a few feet downstream, the exhaust flows in a horizontal direction with a speed of 15 feet per second. Determine the horizontal component of the force that is blowing wind of the force that the blowing wind puts on to the exhaust. Okay, so what force does the flowing wind put on to the exhaust? So what I did was I just assumed that the direction is going to be flowing from right to left. So it's going towards the left. And I just labeled my horizontal. So horizontal just means in the X direction component. So again, going to the left here. Okay. If we label our datum, okay, and we'll get there, we know that this is actually going against our datum. But let's go ahead and move forward for now. Okay, let's label some 1s and 2s. So we always go in direction of flow. Okay, so we're starting out here at the chimney and we're going here, right, downstream. Okay, so that would mean that, so again, given, we're still doing given, that D1 is equal to 4 feet, that V1 is equal to 6 feet per second, okay? And we're given that V2 is equal to 15 feet per second. Okay, so let's see here. We have a couple of other things to think about, and that is that we're given this diameter here, but we're not really sure what this diameter is here. I'm going to leave that there for now, and if we need to solve for the area of that location, we can use conservation of mass to solve for that. Okay, so I'm going to move forward without knowing that information. Oh, another really important thing to note is that since we're in atmosphere at all times, then P1 is 0 and P2 is also 0. So that's also given. Okay, what I want to do first is I want to do a sum of forces onto the system. So since we're only caring about the forces in the X direction, we only need to consider our sum of forces in the X direction. So sum of forces onto the system in the X direction must consider gravity, and then we have pressure, we have viscous, and then we have our other, which I usually just call reaction. Okay, so now, is there any information in the problem statement given about the weight of the exhaust, or, I mean, really anything, right? If we were to, we're only considering the exhaust here, okay? So we're going to draw our control volume to encapsulate the exhaust here. So we actually don't have any weight to consider, okay? So gravity goes away. Now, since we're dealing with open atmosphere, okay, right, P1 and P2 is 0, then we have no pressure forces, okay? Now, we are not dealing with friction, right? Because we're in a completely open system, so we have no viscous effects. That means the only force that we need to consider is our reaction force. And again, if we look at our drawing here, this reaction force, Rx, is going against our datum, which means that this sum of forces onto the system in the x direction is going to be negative Rx. So again, making a note against set datum. Okay, now if you're not sure, if you're not sure the direction, that's okay. You can guess a direction, and if your numerical answer is negative, you've just guessed the wrong direction. It's very similar to statics, right? You just guessed the wrong way. Okay, so that was our sum of forces onto the system. That was our essentially evaluating our free body diagram. Now let's look at a velocity diagram. Okay, so I'm just going to isolate the exhaust. Okay. So we have velocity going this direction is V1, and then velocity going in this direction, which is V2. This is 6 feet per second, and this is 15 feet per second. Now, we only care about the x direction, right? We only care about our x components only, right? Because we're just solving for that horizontal force, okay? So if we break this down, okay, there's no angle to consider in either one of these cases. But at 1, so V1x is going to be 0. It's going to go away, okay? And we can write V1y as just V1, okay? Now at 2, V2x is going to be what? Again, we have to consider our datum here. So redraw the datum. Now, what direction is V2x acting in? It's acting against our datum, which means V2x is minus V2. Okay. And for, completeness, V2y is just 0. Okay, so we draw the velocity diagram to make sure we catch these things, right? To make sure that we're considering the directions correctly. Okay, so now what we're going to do is we do have to solve for our area because we're actually not given any information about area at 2. So we don't know what A2 is, and we know what A1 is, okay? So we can use conservation of mass to solve for our unknown area, and we need to do that because we need it for linear momentum equation. So Q1 is equal to Q2, right? Where Q1 is A1V1, Q2 is A2V2. Rearranging the equation, we have A1V1 over V2, which is going to give us pi over 4, diameter is 4 feet squared, multiplied by V1, which is 6 feet per second, divided by V2, which is 15 feet per second. I'm going to need this calculation later, so I'm going to go ahead and write that A1 is equal to 12.57, and that's going to be feet squared. Okay, so let's go ahead and solve for our A2. A2 is going to be 5.02 feet squared. Excellent. So now let's go ahead and put everything together into the linear momentum equation. So and we're just considering the x direction, okay, where the sum of the forces onto the system in the x direction is equal to sum of rho, directional velocity, x, a magnitude x, and this is all out, minus the sum of density, directional velocity x, a magnitude velocity x in, where in is location 1 and out is location 2. So now let's go, you can go up to sum of forces in the x direction. We already wrote it here, but I don't have to think about it anymore, right? Sum of forces in the x direction is negative rx. So negative Rx is equal to, and this is going to be density V2x A2 V2 minus density V1x A1 V1. Okay, again, adding the subscripts, or I guess adding this notation at this step is really helpful at this step, right? So you're keeping track of everything nicely. Okay, now I'm just going to make the substitutions for my velocity diagram. Okay, so from my velocity diagram here, my V1x goes away, right? This is 0. And from my velocity diagram, V2x is negative V2, okay? So we're going to put that in our equation. So negative Rx is density, and I'm going to substitute here as, negative V2, right? That's what we got from our velocity diagram. A2, V2 minus 0, right? You don't have to put the minus 0 actually if you don't want to. It's gone. Now, after careful analysis, these negatives go away, right? And we end up with our x is equal to rho v2 squared a2. Okay, let's plug and chug, and we get -3 slugs per feet cubed. V2 is 15 feet per second quantity squared multiplied by A2, which is 5.02 feet quantity, not quantity, but 0.52 feet squared. And that is going to give us, Rx is going to be approximately 2.69. And now the units for this is going to be pound force. Okay, if you don't believe me, we can look at the previous calculation here. And let's see here. So this is going to be in units feet squared per second squared. Okay, that's going to get rid of almost all of those. And then we're going to end up getting rid of that altogether with one of these. So unit-wise, this is going to be slugs feet per second squared. Now, from Newton's second law, right, we know that force is equal to mass multiplied by acceleration, and force is 1 pound force, mass, slug, acceleration is feet per second squared. Do you see this? So unit-wise, 1 slug feet per second squared is equivalent to 1 pound force. So we end up with the units of pound force. Okay, and that is the resultant force acting onto the exhaust by the prevailing winds, and we have guessed the correct direction. So it is acting to the left. This is very important that you note this, right? Because we have to make sure you understand the direction. All right, let's do another example. Sorry, in a fresh sheet. So a balloon rocket is suspended from a taut wire by a hollow tube and string. The nozzle forms a 1 centimeter diameter tube, and an air jet exits the nozzle with a speed of 40 meters per second and a density of 1.2 kilograms per meter cubed. Find the force F needed to hold the balloon stationary. Okay, so this is going to be the setup here. You have some wall. Okay, it's kind of sliced there. You have some hollow tube, right, that's hanging on the wire, and then attached to that tube are 2 strings that are then attached to a balloon. Okay. Now, so that's pretty much it. Okay. We are given some information in the problem statement. So we're suspended from taut wire. So this means we have some tension here. The nozzle forms a 1 centimeter diameter tube. So this is going to be 1 centimeter diameter. Okay. And this is air. We're dealing with air with a density of 1.2 kilograms per meter cubed. And it says here that the air jets the nozzle with a speed of 40 meters per second. Okay. Now it says find the force needed to hold the balloon stationary. Okay, this requires a bit of imagination. Okay, let's say you're trying to teach your little cousin a little bit about physics. Okay, and so you build this contraption and you're telling your cousin, or you're teaching him basically, why doesn't the balloon continue on to infinity? Well, it doesn't continue on to infinity because of friction. Well, what's friction? And it raises a lot of really great questions, right? But visually, what is happening to the balloon? Okay, you, for a moment, you've blown it up and you've pinched it. So your finger is right here and you're pinching the balloon. Okay. Now you're pinching the balloon. What happens when you release your fingers, when you release the pinch? What happens to the balloon? Well, in that instant, right, the velocity exiting the balloon, okay, is approximately 40 meters per second. Now, what direction is that balloon moving? It's a rocket. It's moving it's pushing off in this direction so that it would essentially move in this direction, right? It's moving to the right. So the question says, find the force needed to hold the balloon stationary. So logically, if the balloon's trying to move to the right, you need to have a force acting against the movement that is going to the left, okay? Okay, does this make sense? And if you guessed wrong, if you can't visually see it, right, because it's on paper, if you can't visually see it, just make a guess. If your guess is wrong, that's okay. The answer will just come out negative, okay? So again, we have to consider everything relative to our datum. So when we do our setup, that negative is going to come into play, okay? Another thing to note is that this is just going to be x directional, right? We're just talking about the x direction again because the balloon isn't going to pop up, right? It's not being held at an angle, right? It's going to go straight on the horizontal. It's not going to tilt up. So then we only need to consider this force in the x direction. Okay, so the first thing we're going to do is draw our velocity diagram. Again, doesn't matter which one you start with. So you have your balloon, you have an exit here, and let's call this 1. It doesn't really matter what you call it, okay? And this is going to be V1, and again, we draw our datum. So this is going to give us V1 x is going to be negative V1. Does this make sense? Because again, you're acting against the datum here. So you have to make sure that you're considering that negative direction, okay? And V1y is going to be 0, okay? We do not have a y component. Now, this exit is just at, this velocity is just at the exit. What is our inlet velocity? What's our inlet velocity going to be? We don't have an inlet velocity, right? So when we set up our linear momentum equation, that inlet part, it just goes away. And that's okay. If you have nothing entering the system and only air exiting the system, that is okay. Okay, so we're going to also then do our free body diagram, okay, where we have our, again, our balloon, okay, we have our force acting onto the balloon here, and at this point, okay, we know that 1, so this is still 1, we know that this is exiting, okay, to the atmosphere. So we would still draw a Chinese finger trap force that's acting onto our cross-sectional area. So this would be F1. It just so happens to be that F1 is equal to P1A1. But since we're exiting to the atmosphere, we can say that F1 is equal to 0, assuming that we're dealing with gauge pressures, which we can do, okay? So we would essentially neglect that pressure calculation there, so F1 is equal to 0, okay? Now, theoretically, you would have the weight of the air and also the weight of the balloon, and you could possibly have some friction, okay? But unfortunately, there's no information given about, right, the weight, friction, or things like that. So we essentially neglect them. But I'm putting it all here just, as a complete picture. So just to show you that we do consider everything. Okay, so pressure, this goes away. We're dealing with atmosphere. Gravity, there's no info given, right? If the weight of the balloon was given, you would consider it. There's no info given about viscous effects. The only thing that we have to consider is our reaction. So the sum of the forces onto the system in the x direction is going to consider F, but again, F is acting against our set datum. So that would make F, that would make it negative F, okay? Negative force. All right, so now we have everything to kind of put it together and calculate our, and put into our linear momentum equation. Okay, so we have our sum of forces onto the system in the x direction is equal to the sum of rho directional velocity x a magnitude x out minus sum density directional velocity x a magnitude velocity x in. We have no in components, only out, which is at 1, okay? The sum of forces onto the system, again, we've already done it here, is going to be negative F. We have density, we have V1 directional X, A1 V1, right? We already have V1X over here where V1X is negative V1. So this is going to be negative V1, A1, V1. This sign goes away, right? Cancels with each other. So the force is density V1 squared, A1, okay? So plug and chug. This is going to be 1.2 kilograms per meter cubed multiplied by V1, which is 40 meters per second, meters per second quantity squared, multiplied by A1, which is going to be pi over 4 multiplied by 0.01 meters quantity squared, because it said 1 centimeter, get it into the meters. And that is going to give us a force of 0.15 newtons. And just like that, we have our force. Now, again, I'm going to do that kind of unit conversion here. So we have, this is going to give us meters squared, and this is going to give us meters squared per second squared. So that's going to cancel with that. Then one of those is going to cancel with that. And we're ending up with kilograms meter per second squared. And so again, from Newton's second law, force is mass multiplied by acceleration. We have a Newton is equal to kilograms meters per second squared. So similar that we did with the last example, 1 Newton is equivalent to 1 kilogram multiplied by a meter divided by a second squared. So that's how we get our Newton, and that's how we have our resulting force, okay? So those are the examples that I have for this problem, for this lecture. I hope you enjoyed them, and just make sure, if I could say anything, is take your time. So make sure you take your time, draw your datum, state your given, okay, and make sure that you, so take your time, draw your datum, state your given, make sure you draw your free body diagram and draw your velocity diagram, right? Where this will give you the right-hand side, this will give you the left-hand side of the equation, and this will give you the right-hand side of the equation. And make sure that you're considering the datum in both of these diagrams. These diagrams are so key. Again, they take your time and make sure that you're solving carefully and that you are drawing the diagrams carefully, and make sure you're considering those negative signs. If your negative sign is off, the whole thing is wrong. So make sure you take your time. I'm going to keep saying that, take your time, and let me know if you have questions.